maybe after COVID, right? Or
After COVID, yeah.
okay. How's the situation in Ireland now?
It's okay. It's getting better now. We had a lot of cases in the beginning of April,
Uh-huh.
and after the lockdown, the situation improved,
Mm-hmm.
and it's slightly going up in the last 2 3 days. So
Oh, is it
still it
fluctuating?
is there. Yeah.
Is the vaccine anywhere near or
I think yeah, there are a lot of
It's,
vaccine development
I
going
think
on.
everybody is hoping for that,
yeah, we are
but yeah,
planning
nobody
for
knows. Maybe it's
praying.
coming.
Yeah.
Okay, sir. I think we can start. People can like come later. So welcome back, everybody. So hope you had a very fruitful morning session. So now we are having the post-lunch session with Professor Suresh Pillai. So I would like to ask Mrs. Shanti to introduce Professor Suresh Pillai.
Good afternoon, everyone. It's my pleasure to introduce Professor Suresh C. Pillai from Institute of Technology, Sligo, Ireland, to the International Conference on Advances in Material Science and Chemistry 2020. Professor Suresh received his PhD in the area of nanotechnology from Trinity College Dublin, and he has done his postdoctoral research at California Institute of Technology, USA. In 2013, he joined as a senior lecturer in nanotechnology at Institute of Technology Sligo, and currently he is the head of nanotechnology and bioengineering research group. He has also completed an executive MBA from Dublin University in 2009. He was the recipient of several awards such as Boyle Higgins Award from Institute of Chemistry Ireland, Industrial Technologies Award, Holdhouse Commercialization Award, and Enterprise Ireland Research Commercialization National Award. He has published several scientific articles in leading peer-reviewed journals and contributed to many book chapters. He has presented and delivered invited talks in about 40 international conferences. He has also granted 2 US patents, one UK patent, and many more patents are in pending. One of the nanomaterials based environmental technologies developed by his research team was selected as one of the 50 innovative technologies at the first innovation convention organized by European Commission in 2011. He is also the national delegate and technical expert for ISO and CEN committee on photocatalytic materials. Sir, we are eagerly looking forward to listening your talk on new insights into solar and visible light active photocatalysis in ICA MSc 2020. On behalf of Department of Chemistry, Amrita Vishwavidyapeetham, I heartily welcome you, sir, to deliver the talk. Thank you.
Thank you, Mrs. Shanti. Professor Suresh Pillai, it's over to you.
Thank you, Shanti, and thank you, Naveen, for the kind introduction. So let me upload my slides. It's a pleasure to meet you all there. It's a pleasure to meet Professor Padmanabhan. He was my professor at Mahatma Gandhi University several years ago. And my classmate Zina is there. Sridhar I can see there, and I know a few other people in the audience as well. So it's good to see you all. So this is a multidisciplinary audience. So I thought that I should give some introduction to nanotechnology and nanomaterials before I start talking about photocatalysis. So nanomaterials are materials with microstructural dimensions less than 100 nanometers. So what does that mean? People who knows me know that I'm a tall person. So my height is 182 centimeters. So it's equal to 6 feet. So we can consider it's close to 2 meters. So we are going from 2 meters, so bulk size, to another meter. This is my son Sri Shekhar when he was 8 years old. He was exactly 1 meters. So we are going from 2 meters to 1 meter. And if you look around, you might see an ant which is close to 4 millimeters in dimension. So we are going further down. So we are going from meters to millimeters to micrometers now. So if you take some blood and then put it under the microscope, and you might see that the red blood cells will be in the range of 8 to 10 micrometers. So we are going further down into the nano. So if you look into DNA, it would be around 2 nanometers in size. So that is how the size is organized in the biological world. How about materials world? Any material which is under the size of 100 nanometer is generally considered as a nanomaterial. So a nano means, or 1 nanometer means 1 billionth of a meter. Nano means it's 1 billionth or 10 to the power of -9. So 1 nanometer is equal to 1 over 1 followed by 9 zeros of a meter, or which is equivalent to the length of 10 hydrogen atoms. Okay, so let us get a comparison. My hair is a bit thick, and maybe same as many of yours. And I just want you to touch one of your hairs and then feel it. Feel the size of it. You can feel that it is less than a millimeter, isn't it? If you know the dimension of a millimeter in your ruler scale, it is definitely less than a millimeter, isn't it? You can feel it. So it varies to person, but typically the diameter of a human hair is in between 20 micrometers to 50 micrometers. So which is equivalent to 20,000 nanometers to 50,000 nanometers. So how can we get 1 nanometer out of that? So if you want to get 1 nanometer from your hair, you have to vertically slice that into 20,000 times or 50,000 times. And one part of that would be 1 nanometer. So you can imagine how small a nanometer could be. So you are vertically slicing that into 50,000 times, and one part of that would be a nanometer. So we discussed that some of the biological particles are in the nanometer regime and also in the micrometers. So you need a light microscope or an electron microscope to see these particles. The smallest visible length to the human eye is around 10 micrometers across. For example, if you want to see virus, we are talking a lot about viruses now, and also bacteria infections. For bacteria, many of the bacteria you can see under a light microscope, but for virus you need an electron microscope to see it. And also many small molecules, lipids, nanoparticles, you need an electron microscope to visualize it. Nanoparticles has a lot of applications. If you are going out in a sunny day, remember the sunscreen you put on. There are a number of sunscreens available in the market, and a number of nanoparticles are used in these sunscreens. For example, zinc oxide is used in certain sunscreens, and TiO2 or titanium dioxide is used in certain other sunscreens. For example, if you want to protect UVA, zinc oxide is used. UVA is between 320 to 400 nanometers, and in some other cases, if you want to get protection from UVB, TiO2 is used. So that is which will block UVB radiation, which is around 290 to 320 nanometers. Some of you may be expert in sports, or some of you may be playing badminton. you may have seen that a number of recent lightweight sport equipments are available. For example, badminton rackets are very strong and light. So carbon nanofibers are used to reinforce the metal to develop these badminton rackets. And also antimicrobial cloths are available, socks are available in the market based on this nanotechnology. So these are some of the nanoparticles. So before going into the details, I just want to show you some of the products, nanotechnology-based products developed in our lab. The first one is a zinc oxide varistor. This was done in collaboration with Little Fuse, a company based in Ireland. So it's a surge arrestor used in your laptop, mobile phones, etc. So we traditionally or conventionally microparticles are used. So we used nanoparticles to make the size further down. So you can develop or you can get the same kind of properties with a smaller size. The other one is electrochromic display devices. This is done with the collaboration of a company in Dublin, NTRI Limited, and also we worked with a number of other companies such as Vitratiles, radical coatings, etc., to develop different types of products. Okay, so why nanomaterials are important? So you know the surface area of a cube. So it's time to fresh your +2 or 10th class mathematics. The surface area of a cube A is equal to 6a square. Okay, we have a one. So look at the first figure. We have a cube of 1 centimeter. So the total surface area of 6 centimeter square. So I'm going to slice that cube into several 1 millimeter cubes. So the total surface area would be 60 centimeter square. And then I'm going to slice that millimeter cube into a number of nanometer size cubes. So the total surface area would be 60 million centimeter square. So that is the beauty of nanotechnology. The surface area of the material would be significantly higher. So what does that mean? Which means that if you are applying these materials for electronic applications, because most of the electronic applications are based on grains and grain boundaries. So you are creating a number of charge separation units, which means you are creating a number of grains and grain boundaries. So the electrical and electronic properties can be improved. And also in the case of catalysis for catalytic applications, the surface area is very, very important too. So there are a number of ways you can develop these nanoparticles. One is called top-down approach. So you take the cube as we seen earlier, you mill it and machine it down to make it as a powder. And these powders can be further slices down to nanoparticles. That is the way the physical method or the engineers usually do it by milling it. But we are chemists. So what the usual way we make materials through reaction between different types of precursors or by chemical reactions. So we start from molecules. So from molecules, we make clusters and clusters to nanoparticles. So that is the opportunity here for chemists to develop nanotechnology. So if you look into any type of nanomaterials or nanoparticle, chemistry plays a significant role. So a significant part of nanotechnology is chemistry. Okay, this is the reason why, because we start from the fundamental. We start from molecules to make nanoparticles. And the advantage is we can make homogeneous particles. So that is the advantage of chemistry here, or inorganic chemistry or organic chemistry. We use a lot of physical chemistry too. It is a multidisciplinary area with a significant input from chemistry, biology, physics, mathematics, engineering, you name it. So nanotechnology is a multidisciplinary area. So what is photocatalysis? So before going into further, I just want to show you a couple of examples. It's raining outside. You can clearly see it. If you look through your window, what you see? It's a lot of particles on your window glass. Okay. But if you use a photocatalytic glass, and it is already available in the market, it's produced by Pilkington Glass, BioClean. A number of commercial producers are producing this type of glass, and you can clearly see through it. Why it is like that? Because glass is normally a hydrophobic material, so that is what you see here. It's a lot of droplets formed on the surface. So when you use a photocatalytic glass, it is hydrophilic or super hydrophilic, which means that a thin layer of water is formed on the surface. Okay, you may have also noticed this after a hot shower in the morning, and you wanted to look into the mirror in the mirror in the bathroom. What do you see? It's a lot of droplets formed on the or a lot of the steam particles or mist formed on the mirror. So if you use a photocatalytic glass, again, the water will form as a thin film, not as droplets. So it is easy to see. Your reflection will be much better in a photocatalytic coated glass. And it has similar applications in a rear view mirror. Again, it's a rainy day today. What happened when you started your car? It's a lot of droplets, and then you have to take a tissue or a cloth to wipe it off. But if you use a photocatalytic glass, it is easy to, you don't need to do that because it will already be clear. And these type of products are already in the market. So because water is hydrophilic, the surface is super hydrophilic, so water will form as a thin film on the surface. So how does this work? We are chemists, most of us are chemists, so we need to understand what is going on there. So how a hydrophobic surface is changed to hydrophilic surface. All this surface, a semiconductor material is coated on this surface. Okay, and that is called, mainly these materials are from TiO2 or titanium dioxide. So when light hits titanium dioxide, an electron moves from its lower energy level, which is the valence band, to the conduction band. So when some of the electrons are moved from its valence band to the conduction band, Ti is in the 4 state, Ti4 plus. So the oxidation state Ti4 plus will change to Ti3 plus, some of the titanium on the surface. So in order to keep the stoichiometry, some of the oxygens has to move from the surface, which means a number of oxygen vacancies will be created on the surface. And once the oxygen vacancies are created, the water can easily fit into these oxygen vacancies, because water has lone pair of electrons and it can easily fit into these oxygen vacancies. That is how the titanium dioxide will be acting as a hydrophilic or water loving surface. So this is how a hydrophobic surface will be changed to hydrophilic surface. We have published an extensive review on this in 2015. My colleague, one of the senior researcher from Trinity College, Swagata Banerjee, mainly wrote this review, and it is available online. It's published in Applied Catalysis B 2015. Okay, so we discussed that when light hits titanium dioxide, an electron moves from its valence band to the conduction band. So what happens after that? The electron could come back to its original state, and also that is what we call recombination. We don't want that to happen, so I will discuss that in a minute. But once the electron moves from its valence band to the conduction band, we have a hole and we have an electron. So the electron react with oxygen in the atmosphere to form superoxide anions, and water react with the whole to form hydroxyl radicals. So these reactive oxidation species such as superoxide anions and also hydroxyl radicals can react with organic pollutants to form, or it can degrade the organic pollutants or bacteria into smaller molecules to form smaller molecules such as ammonia, water, or carbon dioxide. So it's a simple mechanism, and it's a very straightforward and very powerful mechanism for killing bacteria and also for depollution applications. I just want you to take back to your basic chemistry, your degree or MSc level chemistry. So I'm a chemist, so I need to look into the molecular orbital structure of TiO2. Why this is important? Because if I want to use dopants, I need to understand this. So this is the molecular orbital diagram of TiO2. So TiO2 means it has titania and also oxygen. Then after the hybridization happens, O2p levels are formed, Ti3d levels are formed. The gap between, or the space between O2p and Ti3d are called band gaps. So this is very important. So O2p level, that is the highest occupied molecular orbital, the O2p, and Ti3d, which is the lowest unoccupied molecular orbital. So the gap between these two is generally called a band gap. Okay, so this is very important for understanding the mechanism of photocatalysis and also to design different types of dopants to reduce the band gap. So why we need to have a reduced band gap? We will see that in a few seconds. So I'm going to skip this, the electronic bond structure. Okay, so before that, I just want to give you an idea of different steps involved in the TiO2 photocatalysis. We discussed that the electron moves from its valence band to the conduction band, lower energy to a higher energy. So what normally happens? The electron from its higher energy will immediately come back. Okay, we don't want that to happen because it will reduce the reaction rates. Okay, in order to do that, what we can do, we can use a number of trapping agents to trap either the electron or the hole, so that the recombination wouldn't happen, which means that you can use the electrons or holes for various reactions. So if you look into the time scale, the generation happens in the level of femtoseconds. Recombination happens in picoseconds. Okay, so there are some time limit. But if you look into the trapping also happens in femtosecond. Okay, so if you apply a trapping agent, it will be much faster than the recombination. So we can effectively use different types of trapping agents to improve the reaction process. Okay, we discussed about band gap. Why this is important? Because the band gap of TiO2 is 3.2 electron volt. Look at the equation here. E is equal to Hc over lambda, and lambda is equal to Hc over E. E is the band gap or band energy. And if you substitute all the equations, all the values there, you can see that lambda would be equivalent to 387.5 nanometers. What does this means is that you need a wavelength lower than this to make the reaction happens, or you need an energy higher than this. So which means that if you want to irradiate titanium dioxide or make the reaction happens, you need a radiation which is below 387 nanometers, which is in the UV region. So which means if the band gap of the band gap of titanium dioxide is 3.2 electron volt, which means you need ultraviolet light to make the reaction happen. Is that feasible? For example, we discussed that these materials can be used for different types of disinfection applications. Is this practical? No, it's not practical. If you want to disinfect disinfect an operation theater or a school or a communal area or community center, would it be possible to put ultraviolet light there? No, it's not good for our eyes and it's not economical as well. So in order to make it practical or in order to commercialize this material, the practical way is to reduce the band gap. Again, look at the equation. So if you reduce the band gap, the wavelength can be shifted towards the visible region. So that is why reducing the band gap is very, very important for photocatalysis. So that is the practical way of using visible light for this type of reactions. And also, if you look into the spectrum, solar spectrum, the ultraviolet light is around or less than 5%, and visible light is over 40%. So the efficiency of the catalyst can also be improved by using visible light. So if you want to get more information, we have published a number of review articles. One such example is antimicrobial activity of photocatalysis, fundamentals, mechanism, kinetics, and recent advances, which is published in 2018. My PhD student Priyanka wrote a significant part of it. You can download it. It's available for free. I think it's an open access article in Applied Catalysis B. You can download it to get more information on this. Okay, let us move back to the real scenario. So we discussed that the band gap of TiO2 is 3.2 electron volt, which means that it is very difficult for the electron to pass with the visible light. Okay, so if you reduce the band gap, so if you add dopants in between the valence band and the conduction band to reduce it, which means that it is easy for the electron to jump from its lower level to the higher level. So that is why we have been working on a number of different or identifying a number of different dopants to reduce the band gap. So it's easy for the electrons to jump. So we discussed that the valence band is predominantly made up of O2p levels. Remember the molecular orbital diagram we discussed earlier. And also the conduction band is made up of Ti3d. And we have to, when you are developing or preparing or identifying dopants, you have to have this in your mind. So we have done a lot of theoretical calculations to identify different types of dopants, a lot of DFT calculations. My collaborators and colleagues have done a lot of DFT and theoretical calculations to identify appropriate dopants to fill in between the valence band and the conduction. So it can act as a bridge or act as a step. So it's easy for the electrons to transfer from its valence band to the conduction. So we took a lot of time to understand the mechanism of this. So if you add additional energy level, you can use visible light. So if you look into the figure here, so we have added an additional energy level. For example, nitrogen is doped. So the effective band gap is much smaller. So the electron transition would be easier in visible light. So that is how you can use visible light. So once you have this material, it has a lot of potential applications. Okay, so we can discuss a few applications in the next few minutes. Let me look into the time. Okay. So this is an article published in a Journal of Physical Chemistry Letters in 2014, I suppose. So you can get more information on how we can develop different types of dopants and how we can reduce the band gap and all. I'm going to skip this. And also we discussed about trapping. You need to identify different types of trapping agents to improve the reaction. What happens if the electron moves to the valence band to the conduction band, the electron would come back to the valence band. We don't want that to happen. So in order to get the electron or trap the electron, we can use different types of trapping agents. This is an example of trapping agent used by rutile. In another case, we used anatase and brocade heterostructures, which means that the conduction band of brocade is slightly higher than that of anatase. So which means that the anatase can trap the electron from brocade. So there are a number of ways you can use this type of or develop different types of heterostructures. We also looked into a different type of N-doping or nitrogen doping into pure anatase and pure rutile and see how it affects the visible light activity. This is published in a Journal of Hazardous Materials in 2012. You can download it and get more information there. I don't have time to explain this. The other methodology we tried is to develop oxygen-rich titania, which means if you prepare defects or oxygen defects in between the valence band and the conduction band, you can effectively reduce the band gap. So, is the band gap is narrowing in all the cases? So we did some theoretical calculations and found that it's actually not a single state. It's actually forming as isolated energy levels in between the valence band and the conduction band. For example, the N2P is formed in between the valence band just above 0.14 electron volt. And also the pi star NO is formed at 0.73 electron volt above the valence band. So a number of isolated energy levels are formed in between the valence band and the conduction band. So this is an example of isolated impurity level, which is pi star NO formed in between the valence band and the conduction band. So this is an example of carbon doped TiO2. So we have developed a range of different types of dopants to dope or to make an additional energy level in between the valence band and the conduction band. Okay, so which means that you should be able to use visible light rather than ultraviolet light for this type of applications, or make the TiO2 active in the visible region. So which means that after doping, isolated energy levels are formed. This is an article written by Vinod and published in a Journal of Photochemistry and Photobiology, and this is also available to download. So you can get information on band gap narrowing in anion doped TiO2, and also the theoretical and experimental development of visible light active TiO2 photocatalysis. Okay, so we discussed about using different types of dopants and making this titania active in the visible region. So what are these applications? How we can use it for various applications for real life? Okay, so I'm going to give you an example of this. So why this is important for why these photocatalytic materials are important for hygiene coatings, okay, or to develop a surface which is microbial free. So this is very important because you may have heard about MRSA, methicillin-resistant Staphylococcus aureus. It's a huge cleaning bill for hospitals. A number of people die because of the MRSA infection. So a company in Ireland discussed with us to develop this type of coatings. A company called Vitra Ireland Limited. They wanted to develop an antimicrobial coatings on the surface. So I'll give you an example of this in a few minutes. Before that, the best way to eradicate superbug again is to wash your hand. So we are talking a lot about washing your hand, and this is the best way to prevent any type of microbial infections. Hand and that is the best possible way. And I don't want to give any kind of false information here. Washing hands is the best way and the most appropriate way to prevent any kind of infections. But again, no, hand wash alone will not stop the spread of bacterial or viral infections. Okay, you have to keep your environment free as well. So, for example, if you look into a hospital ward or hospital theater, so this is a typical hospital theater. The wall will be tiled because it's easy to clean there. Okay. So the best way to protect these surfaces is to develop an antimicrobial coatings on these ceramic tiles. A lot of people are canceling their operations because they are feared to go to hospitals. So if we look at the hospital surface, wall paints are there, fabrics are there, ceramic tiles, it's on floors and wall tiles. Developing a ceramic tile, our photocatalytic coated ceramic tile is highly challenging. We started this work back several years back when I was in RRL, Trivandrum, working with Dr. KGK Warrior. Padmanabh sir will know this work. So we started from there, and it was significantly improved since then. So there are a number of challenges of using this type of materials. One is the sintering temperature of these tiles is very high. It's about 1000 degrees Celsius, and you probably know that in the photocatalytic phase. So when you develop the TiO2 in the lab, it is mainly in the rutile anatase phase. So the anatase phase is the photocatalytic phase. And when you heat anatase to a temperature of 600 to 700 degrees Celsius, it changes to a non-photocatalytic phase called rutile. So there are two challenges. So one is obviously the visible light. So you have to develop a TiO2 which works under the visible light. So that's the first challenge. And then the second challenge is high temperature stability, because the photocatalytic phase, which is the anatase, doesn't have a high temperature stability, which means it changes to or transform to rutile at a temperature of 600 to 700 degrees Celsius. So the scientific challenge is, one of my colleagues, Sibu, who is also from Kerala, worked a lot on this one. Sibu, Pradeep, and Reina, and Vinod, they have also Nick, my student, and also Damien, later Kira, and also Rachel, Priyanka. They all worked, and also Sneha. They also worked in this type of materials to make it high temperature stable. So you can see that a lot of research work or fundamental studies went into this type of, or developing this type of materials. So a photocatalytic phase, which is the anatase phase. So if you heat it at 600 to 700 degrees Celsius, a non-photocatalytic phase, which is rutile, is formed. So our aim was to prevent this or slow this. Okay, so we don't want a rutile phase forming at up to 1000 degrees Celsius. Okay, if it or more than 1000 degrees Celsius, because if you can keep the anatase phase at high temperature, that's what we needed. Okay, so we want a high temperature stable anatase phase, which is the photocatalytic phase. So we want to prevent the formation of rutile at the sintering temperature of the ceramic tile. So we have done a lot of fundamental studies. So we used silica, alumina, a number of materials are used, and they are stable up to 1000 degrees Celsius, but because of the nature of alumina or silica, titanate is formed, and the photocatalytic activity is not great for these materials. So titan is no longer pure if you add metal oxide dopant. So we have added a number of non-metallic dopants, or we call it anionic dopants, and some of them are cationic dopants into the titanium. So so that is how you can improve the photocatalytic activity. You can add additional energy levels between the valence band and the conduction band, and also you can make the anodized phase stable at a high temperature. So I'm going to skip that. So this is a work done by Pradeepan Periyat. He was my first PhD student, and Pradeepan did a lot of work on keeping the anodized phase stable. So he's a professor at Calicut University at the moment. So I just want to show one example how this happened. So Pradeepan used very simple technology. Pradeepan used titanium isopropoxide and used sulfuric acid as a kind of stabilizing agent, and then treated this isopropoxide with sulfuric acid, and then a range of different types of precursors are formed, and it was stable up to 350 degrees Celsius, and no crystalline materials are formed, but the dried powder calcined at various temperatures. We can see that the anodase is stabilized, or no rutile is formed up to 700 degrees Celsius. But if you look into normal TiO2 without adding sulfur, a rutile is formed even at a temperature of 700 degrees Celsius. You can see that we have traces of anodized phase even at a temperature of 900 degrees Celsius. This was the first set of reactions we have carried out, and after that we have carried out a number of different types of reactions and identified different types of dopants to keep the temperature stable up to 1000 degrees Celsius, and in some cases the temperature stability was above 1100 degrees Celsius. So that is exactly what we needed to coat these materials on ceramic tiles. So this is an example of or a scheme showing how the phase transition is delayed. So TiO2 is made up of a number of TiO6 octahedra, and then when the sulfuric acid was used, the precursor contains SO4 tetrahedra, and this octahedra was stabilized by SO4 tetrahedra, and then the anodized formation was delayed, and eventually there was no rutile formed up to a temperature of 850 degrees Celsius. So we have carried out, so a lot of our postgraduate students, including Pradeep and Vinod, and a number of our postdocs, Joanna, Nigel, Rachel, and also Kira, lately Sneha, and Nick, Damien. All these people worked on different types of materials, and finally we got a TiO2 which is stable up to close to 1000 degrees Celsius or above. So now we have a range of materials, and after that two of our postdocs came up with a novel solution, and we have tried that, and we have filed a patent on this. And when we coated these materials on a normal tile, on a tile, what you see here is no bacterial growth. This is on the right hand, and when you look at the left hand on the petri dish, a number of bacteria formed on a normal tile. So it shows that the photocatalytic active material is effective against a range of bacteria. So we have also carried out the testing outside and saw that 99% or 99.999% of the bacteria were killed on the surface. So the mechanism again is straightforward as we discussed earlier. When TiO2 is used, after the irradiation, the electron moves from its valence band to the conduction band. A range of reactive oxidation species are formed, and this react with bacteria, and the membrane can be ruptured, and also it can react with the cell materials, and the bacteria will eventually be killed. So a US patent was awarded in two US patents were awarded, one in 2013 and the other one is 2015, and another UK patent was awarded in 2015, and we have a number of other patents pending based on these technologies. And after the successful laboratory studies, we have developed these tiles commercially. So we have been working with a company in Arklo. Their headquarters was in Turkey. So we developed a range of ceramic tiles, and this technology was identified as the 50 innovative technologies from Europe in 2011. And also after this, after 2011, we have carried out a range of studies, and we have we came up with an optimum material, and we got a patent awarded in 2015. And after that, this got a lot of international attention. This was highlighted in the Guardian newspaper, the Times, and also BBC. A range of international media covered this news of developing these coatings to ward off the bacteria. And this technology got innovation award in overall Irish Times Innovation Award in 2017. Okay, I think I'm running out of time, so I just want to summarize it. So we discussed about the simultaneous production of visible light activity and high temperature stability. So antimicrobial ceramic tiles were developed using this technology, and this was effective against a range of bacteria, including E. coli and MRSA. So the funding was mainly obtained from Enterprise Ireland, Science Foundation Ireland, and also we had a US Ireland project partially supported by National Science Foundation. And I have strong collaboration with a number of organizations in India. We have currently have a European DST project with BITS Pilani and also NERI in Nagpur, and also a number of academic organizations and industries in Europe and India. So thank you for your attention, and I'll be happy to answer your questions.
Thank you very much for your spectacular presentation, Professor Suresh Pillai, and thank you for sharing your questions. I think we can take questions. If anybody has questions, please raise your hand so that we can take questions one by one. Does anybody have questions? See some.
Hello, sir.
Yes. I see.
Sir, there are different transition metaloxides are there performing the photocatalytic activity.
Yeah.
So your work is mainly focused on the photocatalytic activity of titanium oxide, and we are adding doping to decrease the band gap and other activities. Can we extend these studies into other transition metal oxide which is capable to produce electron and holes that is visible active transition metal oxide?
Yeah, it's a very good question. So the question is a number of other transition materials are available. Can we extend that to the study to other materials? So obviously, yes, a number of other materials have been used, including metal oxide, chalcogenides have been used. But titanium is identified as the optimum material for the time being because of its availability and also non-toxicity. If you look in the literature, you can see that significant number of studies have already done, including zinc oxide, zinc sulfide, a number of other chalcogenides. But for the availability and toxicity reasons, titanium is identified as the optimum or the suitable material for this type of applications.
Thank you, sir. And also I have one more question, that photocatalysis and the phenomenon adsorption, is there any connection between these two things? Because in the antibacterial activity, the bacteria should be adsorbed on the surface of the tile, and also suppose in the photocatalytic degradation of what organic pollutants present in water, is there any connection between the adsorption? Because first of all, the organic pollutants or bacteria should be adsorbed by the catalyst, then only it can decompose, I think so. So is there any connection between these two?
Yeah, obviously, the adsorption plays a significant role in photocatalysis, particularly for dye degradation and all, or any type of chemical compound degradation. The adsorption plays a significant role. But in the case of bacteria, it should be. I don't think the adsorption plays any kind of significant role there. You need the bacteria on the surface. And then once the bacteria is attached to the surface, then it's not an adsorption reaction. So it can, the reactive oxidation species can work towards this, the biological species. To make it short, for chemical reactions, it's very important, but for bacteria, I don't think it plays an important role.
Okay, thank you, sir.
Okay. Are there any more questions?
Yeah.
Yeah, I see. Yeah, Padmanabhan sir. Okay, sir, go ahead.
Sorry, Professor Suresh, I missed your second part because it got disconnected. I joined again now. Okay, so you talked about the nitrogen doping. So you're creating a hole there, right?
Yeah.
I mean, you're nitrogen replacing oxygen. Was it successful? Because there are a lot of other issues also, the charge-wise, and has it been achieved? Could you replace part of oxygen with nitrogen and then get a hole created and then make it function? Or because you did some calculation, I guess. I mean, at that time I lost connection.
Yeah, you are actually not replacing oxygen. It's a different types of dopant. So when we studied XPS, we found that there are a number of different types. So can I show you an XPS spectra? Just one minute.
Sure. Yeah, but I'm wondering, why does it go in the cavity? It cannot go in the cavity as a nitrogen cannot exist as such. Only N2 can exist. So
yeah,
it will be so, and also charge-wise, it should replace some oxygen. I thought. So of course, XPS would tell you the presence of nitrogen. Definitely yes.
Yeah. But it's not then, actually replacing. It's actually. Sorry. Can you see the?
I see your.
Sorry, it's a different one.
A different slide, yeah. A different slide.
Can you see it now?
Yeah, I know. I don't. I mean, I can't see. I don't know about others. So I see your occupation safety health.
Okay, it's the wrong slide I selected.
Okay. It's okay. You can tell me. XPS, I know you get information about the nitrogen. That's fine.
Yeah.
But only thing is, I'm just wondering what the nitrogen. Where does it go into? I mean, cannot go into
It's
cavity
it can go, in three ways. It can go dope into the material. So one is it can be interstitial nitrogen, and also it can go into the surface, and also so lattice nitrogen, interstitial nitrogen, and also it can be on the surface. So three ways nitrogen can dope into the titania.
Does it bring down the band gap? You have tried probably.
Yeah, it will reduce the band gap, of course.
How much is the nitrogen content? Is approximately maybe 1% or?
Oh no, less than 1%. It's 0.05 in some cases.
Okay.
Yeah.
Very difficult to replace.
Yeah.
So it brings down or just pushes up. Band gap increases or decreases?
Band gap decreases.
Okay.
And also we have another example of band gap increases in the case of rutile. We found that the band gap actually increases.
Okay.
I can send you that papers.
Oh, okay. Thank you very much. Sorry, I missed the in between actually, so I just got disconnected.
Sir, can I ask one more question?
Yes, sir. Go ahead.
Yeah, sir, I'm Adarsh.
Dr. Adarsh. Okay.
Yeah. Sir, I have a question regarding that superbug. I think I already heard you from the same. So I just wonder if you are replacing. You told that the reactive oxygen species is responsible for the destruction of the superbug, right?
Yeah.
Yes, sir. If you are replacing because the reactive oxygen species from TiO2 is a kind of superoxides. I mean, the type of reactive oxygen species from the TiO2 film, whatever is responsible is superoxide, or which kind of reactive oxygen species is responsible for?
It's, hydroxyl radicals, superoxide anions,
okay,
and also hydroperoxides.
Okay,
hydrogen peroxide can also be produced. So these are the different types of reactive oxidation species.
Yeah. What? Okay. So what
water. Yeah, I think the aqueous condition actually you need to have it.
Yes.
Water.
So what I wanted to ask you that if you are replacing the titanium oxide with some of our organic sensitizers, which can produce singlet oxygen excessively, and which is more, powerful reactive oxygen species. Right. So what you are thinking that if we can apply the same to the this kind of applications? I mean, for the photosensitizers, organic photosensitizers with the so that we can completely get rid of the use of this costly materials and all those things, no?
Absolutely. That's a very good idea. But singlet oxygen, if you can produce singlet oxygen, that is more effective than any other reactive oxidation species in case of for the degradation of bacteria. And singlet oxygen was found to be one of the best reactive oxidation species. But the problem with the ceramic tiles, you cannot use any kind of organic reagent because these are heat rated at very high temperature.
Okay.
For ceramic tiles, it's not practical, but other reactions, if you are using a low temperature material or your low temperature reaction, absolutely, this can be useful.
Okay, sir. Okay, thank you. Thanks.
Yeah.
Okay.
Are there any more questions? Okay, if not, then let's all thank Professor Pillai for his wonderful talk. Thank you very much, sir, for your time and the presentation.
Thank you, Naveen, for the invitation, and thank you, Professor Padmanabhan, and also Naveen for the kind invitation to give a talk. So if you have any further questions, you can contact me and I'll be happy to answer. And most of this work is available to download from the website or Google Scholar. Most of these articles are available open access. So feel free to download. And thank you again for your attention.
Thank you, Professor Suresh. And please do visit us sometime when you come down to India or Kerala.
Absolutely. Yeah. That's in
Professor
my
Mangalam.
list.
Yeah, Professor Mangalam, are you there?
Yes.
Okay, I think we should invite him. He can inspire our students.
We would have loved to have all these people personally coming to our place. We could have given them good food.
Yeah.
They would have seen our campus.
Yeah.
All
next
that.
time.
Yeah, next time. Please do come.
Okay, so this
Thank
is
you.
the time. Thank you, sir. So this is the time to close the today's session. I hope all of you enjoyed all the talks, and then I'm sure there was a lot to take home and think about, and then relook into the research we are doing currently. Now I think it's time to go to the oral presentations. We have given you the different links for different streams running. Today, the first day of the meeting, we are having 2 streams parallelly running. As you know, we're having inorganic chemistry session and the electrochemistry session running parallelly. So the links for joining these oral presentations are given here. I also put it in the chat session if you want to access from here, or you can go to the website, the conference website, and get the access to these oral presentations. So I wish you all a very good day. I hope you enjoyed the event. So see you again tomorrow morning at 8:30 a.m. sharp with Professor Boris's talk. Bye, everyone.
Thank you, Naveen. Thank you so much.
Thank you, everyone. I'm sure I am.